Okay, so in this problem, what we have is there's someone standing on top of a 22-meter tall building right here, and they're throwing a baseball at 12 meters per second at a 53.1 degree incline above the horizontal. This is phi. And yeah, so they're throwing this baseball. What we want to know is what is its speed right before it hits the ground, okay? So what we're going to do is because we're in the section involving energies, I'm going to try to solve this two ways. One, using energy formulas, kinetic, potential energy. And then the other way I'm going to solve it is using standard kinematics formulas, all right? Okay, so let's go here. So what I want to do is because I want to solve this using, like I said, energy formulas. Let's do this. So let's say I'm going to just redraw my building here, okay? And the ball is going to be thrown here. It's going to go in this ballistic trajectory. And it's going to hit here. So initially, the ball has some potential energy. I'm going to call it PE0, which means its initial potential energy. So because it's 22 meters up above, our reference point is the ground. So from a potential energy perspective, our reference is just the ground. So compared to the ground, it has a plus. It's up 22 meters. Now, it also has some kinetic energy as well, too. Because the ball is being thrown, meaning it has a velocity. So the ball is up on top of a building, potential, and then it is being thrown. It has a velocity as well, too, so that's kinetic. So these things, which is the total mechanical energy of the ball is the potential plus the kinetic. Once it hits the ground, or right before it hits the ground, its potential energy is gone because it's essentially at the ground or almost at the ground. So its potential energy is effectively gone. But it's going very fast though, right? So all that potential, the initial potential plus kinetic energy, is being converted into a final kinetic energy. Okay. So what we can do is, and these are the only energies involved in the system. We don't have thermal or chemical or nuclear energies. All we have. This ball only has potential or kinetic energy. So because of that, we can just solve this formula using that. So we can say well, actually, let's go back. I want to start with this one first. So I'm going to start off with the initial kinetic energy, KE0 initial, plus the potential energy, 0, equals the final kinetic energy, okay? So kinetic energy, of course, is 1/2 mv squared, and then potential energy, of course, is mass times gravity times height, and then kinetic energy, of course, is 1/2 mv squared. Now, we can multiply everything times 2. This gets rid of that 2. That gets rid of this 2. It puts us a 2 here. And we can divide everything by m, which gets rid of that m, and that m, and that m, and that m. And so we end up with v squared plus 2gh equals v squared. Now these v squared, this is the initial. This one here is the initial, and this one's the final. Now the final is what we're looking for. So the initial velocity, it told us that, is 12 meters per second. So we say 12, we square it, which is 144, plus 2 times gravity, 9.8, times height, which is 22 meters. And then, of course, this is equal to v. Of course, we have to take the square root of that, right? Because we have to take the square root of v squared. And if you do all that, you end up with v equals 23.983 meters per second. Okay, so that's how fast the ball is going. Now, this doesn't tell us the direction the ball is moving in, right? Because the ball could be, going this way, or it could be going this way, or it could be going this way, or it could be going this way. So this formula here doesn't tell us the direction of the ball. It only tells us the speed of it, which is the length of this arrow. So it's telling us the length of the arrow, but it's not telling us what direction the arrow is pointing in, okay? So when it has these, 1/2 mv squared, for example, the v just means, the v doesn't mean the speed and the direction. It just means just the actual speed itself, okay? All right, so we have which is what we want. We're just looking for just the speed, and this is just the speed. Remember, speed is like the absolute value of, because this is a vector here, and so you're just saying I don't want the actual direction of the vector. I just want like how long or the length of the vector is. All right, so that's great. So we just solved this problem using just energy formulas, kinetic and potential, i.e. mechanical energy. Now let's try to solve this using standard kinematics formulas, okay? So what I'm going to do is I'm going to look at this thing I'm going to look at the velocity of this ball, right? So let's draw a little building here, and the ball's going to go up like this, and then it's going to come down like that. So let's look at this from a kinematics formula perspective. Let's look at y, the velocity in y, and then we'll figure out like how long did it take? You know, what was the time that it took for this ball to go from here to here? Okay, so let's do that. So let's create a graph here. This is velocity in y, and this of course is in meters per second, and this is our time graph. Now, what we need to know is because I'm looking at velocity in y, if I come back up here, you can see, maybe I'll change this to a different color, maybe blue, is I can take this right here and I can do 12, which is the length of the vector, times the sine of 53.1 degrees, and I can get 9.596 meters per second. That's in the vertical direction. And the horizontal direction, it's 12 times the cosine of 53.1, and you get 7.205 meters per second. So we've taken this vector and we've broken it into two components, 9.5 meters per second and 7.2 meters per second. Great. So because we know that now, we can take our velocity in y and say, what is the initial velocity in y? And we'll just write it right here. And that was 9.596, of course, meters per second. Now, so that's the initial velocity, but how is the velocity changing? Well, the only force on this baseball is gravity, and gravity is pulling down at 9.8 meters per second, negative. So we have a linear equation because it's pulling down linearly, like this. And so the slope of this, so this function here, well, the slope is negative 9.8 because that's the force of gravity. That's its acceleration, or you could think of it as deceleration. So this function here, the velocity as a function of time, is equal to our slope, which is negative 9.8 meters per second. Now it's t times t, right? Because every second, the velocity increases by that amount. So at 1 second, it's 9.8. At 2 seconds, it's 2 times 9.8. At 3 seconds, it's 3 times, et cetera, et cetera. So the velocity, of course, is increasing as the time ticks by. Okay, let's do this as well too. All right. And at some time here, maybe make this like this. At some time here, whatever time this is when the ball hits the ground. So this is here. Ball hits ground. Ball hits the ground. Or it stops. What point is this right here? This is when the ball is, it says this is where the velocity is 0, right? Where's the velocity 0? At the very top. The very top. So remember the ball's going up, 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 up. And so right before it starts heading back down, its velocity is 0. Because here, its velocity is positive, meaning it's going up. It's positive, it's positive, it's positive. It's slowing down, slowing down, slowing down. Now it's at the very top of its trajectory, and now it starts going down faster, 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 until it hits here. Until it hits here. Okay, and we may want to know like its speed too. Okay, when it hits the ground. So this point here is the speed, this velocity, when it hits the ground. Okay, so one question we could ask is what is this area here? I don't know, but it's the distance from when you throw it the point of from where you throw it to where it hits its peak up in the air. Okay, so and then when it comes back down, let me actually maybe just change this to a different color, like right around here, roughly speaking. Maybe let's make this a green color. But, sorry, yeah, this is what I want. Okay. So let me actually show you what this is. Let me erase this. I want to redraw this just a little bit more exaggerated, just to make it more obvious as to what's happening. Okay, so here we are. We have a building, right? The ball's going up, and the ball's coming down. Okay, so this yellow part over here is this. So that's this distance here. It's the vertical distance. That how much vertical distance did it travel? See this yellow part here? That's that part. How much vertical distance did it travel? So that's the area under the curve. The area under the velocity versus time graph is the displacement. How much did it get displaced? And here we're talking about vertically. And then the green part over here is when it's coming back down, right? This part here, right here. That's where it's coming back down, which is this part right here. But then the ball, so the ball's level, right? At this point here, right, the ball is level. And so then it needs to travel an additional this distance here. And what's that distance? Well, we're 22 meters up, so this part here is 22 meters, which means this part here is 22 meters. It's like it's negative because anything under this graph, anything under the zero line is considered negative area or negative displacement. So yeah, and it kind of makes sense, right? Because you're kind of, because the origin is the ground, right? The origin is the ground. So because you're going here in this direction, it's considered negative. If you're going in this direction, it's considered positive. Okay, so this is quote unquote our negative, our area, so to speak, is negative 22. Okay, like actually area isn't negative, but from this mathematical perspective, because it's lower than this line, it is negative. So check this out. This area here, or this time, or whatever this distance is, which happens to be area here, this distance here is the same as this. It's the same as this, right? It's the same distance, right? This is the same distance as this. So whatever this is, maybe this is 10, this is negative 10. If this is 20, this is negative 20. So these effectively cancel each other out. So if I wanted to know what the total area was from here, from 0, all the way to when it hits the ground, that's 22, right? Or negative 22, because these two cancel out. So the only thing we're left with is that. So now we have a calculus problem, an integration problem. So we can say negative 22, that area is the integral is equal to the integral from 0, so from time equals 0 to a. I don't know what a is. This is what we're looking for. A is where we're looking for, right? Right here. That's a. Of the function, oh, I didn't finish my function up here. Negative 9.8t plus our starting point, our initial conditions are 9.596. That's the whole function. So let's just do that. So that's the, it's v of t, which is negative 9.8t plus 9.596. Okay, so we have negative 22 equals the integral from 0 to a. A is the time when it hits the ground. Of the integral of negative 9.8t plus 9.596, and this is relative to d, so we're going to say dt. Okay, and then all you have to do, this is just a standard integration problem. All you have to do is just solve for a. That's what we're looking for. Right? You just have to solve for this guy right here, and once you do that, you'll get a equals 3.313, and this is seconds. So we know that the ball hits the ground at 3.313 seconds later. Okay, so that's cool. So if I know that, and I know the function that I have, the velocity as a function of time, so I know its velocity in y as a function of time is equal to, once again, negative 9.8 t plus the initial conditions, 9.596. And all I have to do is take this a here, swap it in, right? So now it's the velocity of y as a function of time, but now the velocity of y, and I'm going to pass in 3.313. So that's negative 9.8 times t, which is 3.313, plus 9.596. And if you do that, you'll end up with a negative 22.887. Okay? And this, of course, is in meters per second. So the negative here actually makes sense because this is velocity in y, and so y only goes up or down. And so if I say negative, I mean I know this is the downward vector, meaning the vector is not pointing up, the vector is pointing down. So basically, I know everything about this particular component is that this vector is pointing down and its length is negative 22.87. Now, I only have one component of the velocity vector. I still need to know, if I want to find its overall speed, I need to take the velocity vector plus the horizontal, I need to take the vertical component and the horizontal component and put those together to get the overall speed. And I know the horizontal one, that's velocity in x. Is the velocity in x a function of time? No. Because if I come back up here at the top, you can see as the ball is going here in just the x, it's x velocity. Is the x velocity changing? Meaning, is there something that's changing it? No, nothing is changing it. Gravity changes the y component. It doesn't change the x component. So whatever the x is, which is 7.2, it's just continuing along its merry way. 7.2, it's going to be 7.2 here, 7.2, 7.2, 7.2, 7.2, 7.2, forever until it hits the ground, and then of course it's going to stop. But it's going to be it's a constant 7.2. So the velocity in x is 7.2 meters per second, right? Because it never changes. So what you can do then, if you want to find the overall velocity, is you just put these two things together. The velocity in y is, and we'll just start from here, is going down at negative 22.87. And then the velocity in x is a positive 7.2, which looks like this. So we're going to go from here to here. We're just adding these together. We're going to take this component, the vertical component of velocity, and then this is the horizontal component. We're just going to add them, right, tip to tail, right, like this. And this guy here is 7.2, okay, and that's positive. And if you do that, you'll get your overall velocity vector, which looks like this. This is the overall velocity vector here. And so this is its actual direction. If you wanted to find, you'd have to do some trigonometry here. Obviously, this is a right angle, and then you have both sides. Actually, you have all three sides, right? You just take 7.2. If you want to find the length of this other side, how would you do it? Well, it's Pythagoras theorem, right? A squared plus b squared equals c squared. Equals c squared, right? And then you take the square root, get rid of this square thing here. And so then c, which is our hypotenuse, is equal to a squared plus b squared. A squared is negative 22.87. B squared is 7.2. You square those, right? Add them together. And you get 23.9. So the length of this vector here is 23.9. And if you look back up here when we were doing our energies, 23.9. So it turns out that using our kinematics formulas, I got the same answer. This is our kinematics formulas. Got the same answer as using the energy formula, which of course is something that you would expect. But here, one thing is now we know we could find out what this angle is here. Okay, if this is 0 here, if this is our primary axis, then we could find out what this is, because this is the right angle here. We know this length, we know this length, we know this length, and like I said, using just normal trigonometric formulas, we can find out this angle if we want. That's trivial. Okay, I want to leave with one final thing. Let's imagine I have my. Let's just draw this again. Let's say here's my building, and I wanted to know. So you're starting here, and I wanted to know how high up this is. Right, this distance here, x, and we'll call it in meters. I want to know. I want to know. I want to know what this is. But I want to use it. Now, of course, we've done this before using kinematics formulas, but I want to know what it is using just energy. Okay, so if you wanted to know that, you could say, okay, well, there's a certain amount of kinetic energy here, and that kinetic energy is going to get converted. It's going to bleed off, bleed off, bleed off, bleed off until there's no more kinetic energy. And now all we have here at the top is just potential energy. So what I could say is that my kinetic energy, initial, should equal to the potential energy at this point right here. So the kinetic energy, like I said, will it's some amount of energy, and it's going to bleed off, bleed off, bleed off until it's gone. But it's all been converted into this potential energy right here. But the trick to this is that it's not all of your kinetic energy. It's the vertical. In this case here, we're only looking at the vertical component of the energy. So, or the vertical. Basically, what you're looking at is the vertical velocity, which was 9.5. So you're not going to do. It's not the kinetic energy of 12 meters per second. It's a kinetic energy of 9.5 meters per second. Because this energy, yes, the vertical part will bleed off, and it will be right here. There is no vertical, right? There is no vertical velocity here, but there is still horizontal velocity, which means you still have overall kinetic energy at this point right here, because the ball is still moving in this direction. So there is an overall, quote unquote, overall kinetic energy, but its vertical energy is gone. So what we're going to do is we're converting the vertical energy from here to potential energy. Does that make sense? Because it still has horizontal energy. So if you do that, then you could say kinetic energy, of course, is 1/2 mv squared. Potential energy is mgh. You can divide by m, get rid of this, and then multiply by 2. So this would be v squared. Well, you don't have to. I mean, whatever you want to do. You could say, if you wanted to multiply by 2, you could get rid of this, and so this would be gone, and so you would have v squared equals 2 gh, something like that. And then we're looking for our height, remember? So we could divide by 2gh, and so therefore then height is equal to v squared over 2g, where g is gravity. And then remember here, v is not 12 meters per second. We're just looking at just the vertical part, because it still has remember, at the top here, I know you already told me that. At the top here, it's still moving in this direction, right? So it still has kinetic energy. It just doesn't have kinetic energy in the y direction. I mean, there's no velocity in y. Okay, so once you do that, you'll have so v squared here. This v squared is 9.5. So you do 9.5 squared over 2g, which is 9.8. Blah blah blah. And that's h. And if you do that, you'll get h equals 4.6 meters. And so now, using that, you could come back here, because it's 4.6, and you could say this area here is 4.6. And if this area here is 4.6, that means this area here is 4.6. And so there you go. All right, so once again, just to recap, we use the kinetic energy formulas to find out the final distance. To find out the final speed, but we really don't know its direction, because these formulas here don't tell us direction. They just tell us just its actual speed, the actual speed. But using these kinematics formulas, we also verified the speed, but we were also able to find its but we were also able to find its direction as well. And then finally, you can use the kinematics formulas to find, these energy formulas to find, for example, just the height. But you have to remember, if you do that, you would only look at just the vertical component of the velocity and not the overall, because here it still has a horizontal velocity, so that would be bad. If you use 12 in your v squared thing here, you're gonna get the wrong answer. So you have to make sure if you just want to know like how high up did it go, you're just looking at the vertical component of the velocity and not the overall. Okay, that's it.